about this material, and after that we will go to the nonlinear nonlinear behavior. So as you remember, linear elastic analysis usually provides the big assumption that displacement is linear according to the stiffness, and this is enough for simple engineering calculation. But as you know, real world is not linear, and every mechanical response from every system is not linear. So this refers to material and geometrical non-linearity. Okay, so you can find a lot of examples in every type of industry where the non-linearity appears. So if you take a look on an automotive industry, you can observe a lot of non-linearities in, for example, suspension systems, gears, cabin frames, gaskets, and these examples, you can observe, let's say, these are examples where non-linearity plays the main role, we can say. And on the next picture, I would like to introduce to you the non-linear material characteristics which is available in Midas and FX. So for today we can analyze elastoplastic material models and hyperelasticity. So if we consider this type of material, which is commonly used for the metals, we can consider yield criterion, which comes from the von Mises theory and is also valid for the metals. And the other thing is that every kind of these nonlinear materials require entry. So in this case, we can provide this nonlinear data using, let's say, stress-strain curve. We can provide this nonlinearity data using plastic hardening curve, and we can use the perfect plastic model, which is the third type, which is supported by Midas and FX. And all of this plastic range, let's say, supports the hardening rule, which is divided into isotropic, kinematic, and combined. And also, if you take a look on the function, Midas and FX provides you the temperature dependence and strain range dependence, which is often called as creep. So let's take a look on the material curve, and just to remind you the basic theorem. Now we see the engineering stress-strain curve, and this is the graph or plot, we can say, which you are familiar with your everyday work. So this is how does it look like, the relationship between the stress and strain. This graph is provided from the simple, let's say, tensile test. And what is important for this curve, that the values of stress are provided as the according to the original cross-sectional area. So this is the basic formula to describe the nominal stress. And this value is often provided as the in regard to the original cross-section. So this is an important thing. And the second curve is the true stress-strain curve, which provides you the real stress-strain relationship for your specimen. So this time the behavior is characterized by actual force divided by actual cross-section area, and the total strain is calculated using this formula, which equals to natural logarithm of instant gauge length divided by original gauge length. And if we make some assumption which refers to the constant volume, and this is this equation, we can provide following relationships. We provide you the connection between the engineering data and true stress-strain data. In let's say nonlinear applications, it's very important to convert this engineering data to true data, And on the next slide, we see some example for that. So all you have to know that if we want to convert our data which comes from the test, we can use the previous formulas, and the linear interpolation will be used between the points. So for example, in this case, the engineering data is the curve below, and at the top we see the true stress curve. Of course, I didn't mention this at the beginning. You can ask some questions during the presentations, and my colleagues will answer to you using the chat section. And I will answer about the one question, because somebody is asking that is it possible to get the presentation? Yes, it is possible, and we will send you the material and also the recording after this meeting. So this is the example how to convert the engineering data into true data. And on the next slide, we see some graph which refers to the work hardening. And if you remember from the fatigue analysis, the behavior from point A to point B describes the plasticity. So in the simple linear static analysis, what is important according to the material is the point from 0 to A. So we are considering this range, and this refers to the elastic stress and elastic strains. And in the nonlinear analysis, we have to consider this range from A to B. And this part on the curve is characterized by this Holomos equation. So this is the formula which is used. So if you have this data, which refers to the strain coefficient and strain hardening, you can provide this curve into Midas and FX, and this will be very useful if you want to use the plastic hardening curve. So at the bottom of the page, we see some properties of the steel, so it's easy to get this information. And on the next slide, shows us how the input looks like in the NFX. So to the left, we see the stress strain curve. So this data is entered using this option. So if we click on this stress strain curve, we have to define the function. We have to have defined the function first. So in this case, we have to provide this data, and as I mentioned, it will be good when you provide the true stress strain data. And the second option is to enter the plastic hardening curve, and this curve starts from the plastic range, and you can use this Holomos equation to provide to plot this curve actually. And why we need nonlinear data? So sometimes this work hardening is required, sometimes don't. So in case that this work hardening is desirable, we can perform a lot of simulations according to the metal working processes that induce a plastic deformation, because we are looking for because we want to exact a shape change. So these are following examples, which refers to the rolling, bending, shearing, and drawing. And in the Midas and FX, it's actually easy to perform this type of simulation, and I will show you later how to do that using the simple metal forming. On the next page, I would like to briefly introduce you the nonlinear analysis types in Midas and FX. So Midas and FX supports the nonlinear static analysis, nonlinear dynamic analysis, and analysis which is called quasi-static. And in a static analysis, let's say like a stress analysis FEA is done using the simple, let's say linear equation, but in the nonlinear analysis, the stiffness matrix is nonlinear. That's why we are talking about this, that this is nonlinear analysis. So, but the relationship is quite simple, and if we consider the velocity or acceleration or some other inertia forces, of course there is no there is no inertia forces and the velocity is 0. In case of the dynamic analysis, we have to solve this equation, which is differential equation. And as you see, it's much more complex to solve. I hope I don't have to clarify the symbols, but these, let's say, dots indicate the time differential. So in the all dynamic, if we want to consider the dynamic response, we have to provide to the system some input in the time domain, and of course output will be provided in the time domain. And the last type of the analysis which is supported by NFX is the quasi-static analysis, and this is actually a special case of the dynamic analysis, and it's much more close to the nonlinear static analysis. But what's the difference? The difference refers that to calculate this analysis, we can let's say assume that the static laws are constant in time, so the velocity of acceleration will be constant. So we will never get the response like that. And in Midas NFX we have following analysis, nonlinear analysis types. So you can perform simple nonlinear static analysis, which refers to the geometrical nonlinearity and material nonlinearity and contact as well. The second type is nonlinear quasi-static. The third type is nonlinear implicit dynamic, nonlinear explicit dynamic. The difference between them is the difference between them refers to the integration method according to the time. And the fourth type is the sequential nonlinear, which is actually a combination between all of these three types. So if you take a look on the picture to the right, sequential analysis provides you the capability to solve the problem using let's say three cases or three steps, which will be based on the nonlinear static, nonlinear implicit dynamic analysis, or nonlinear explicit. So it's up to you and your case what will be the order in this analysis, and how you will make your process. So that's all about it. And on the next page we see some examples according to the nonlinear analysis in Midas NFX. So we can consider quasi-static as the simple nonlinear analysis or dynamic analysis. So actually quasi-static analysis is a special type of analysis which can be solved using implicit and explicit method, and this refers to this nonlinear analysis types what I showed before. So in some cases, actually in this case both methods are allowed, but we have to remember that some assumptions should be made for the explicit method, because this method has been provided as the true dynamic method, but in this case we have to assume few things to analyze this type of problems. So on the next page we see some simple explanation between the implicit and explicit approach. So now just to remind you, I'm talking about the dynamic analysis. So at this moment let's forget for a while this quasi-static. Now I'm talking about the dynamic approach, about dynamic approaches actually. So if we consider the implicit time integration, we have to remember that this method focused on the displacement by inversion of the stiffness matrix. So if you remember this equation from the previous slide, to calculate the displacement we have to inverse. Right? Force vector is divided by the stiffness, so we have to inverse this, and this process is very, let's say, it's very problematic and cost for your CPU and for your memory. That's why not every kind of problem will be valid to solve using this method. And this method also refers to the to the problems, let's say, slow dynamic problems, which means that the response is between, for example, 100 part of the second and more. No, is, let's say, never less than 0.01 second. And explicit time integration is a method which focuses on acceleration, and you know this equation from the second Newton's rule for the dynamics. So this time the mass matrix is inversed, and this is much more easier for your CPU and for your memory. That's why we have a lot of advantages, and calculation can be obtained much more faster. So this is the difference between these two approaches. But for some cases we can use this actually in terms of modeling material nonlinearity. We can use all of these methods to simulate a lot of class of problems. So in this case you see the role former, and this example has been made for nonlinear implicit analysis, and I think you don't see the next slide, so I have to wait a little bit. So could you answer me, do you see the example, or you see still the page with the implicit and explicit? Oh, I think right now it's fine. So you're supposed to see the animation for the role former, and this analysis was done using nonlinear implicit time integration. And of course some material nonlinearity has been specified. And now I will show you another example, and this refers to the riveting process, and this example was made using the explicit. Sorry for the mistake on the slide. This should be a nonlinear explicit. And in this example, as you see, we used also our new feature, which is called element dilation feature, and that's why this part is broken. And at this moment, I think I will switch to the Midas and FX, and we will make simple example for the metal forming, and for the simple object, which is a plate, and I will show you how to set up this analysis inside the Midas and FX environment. So let me switch to the Midas and FX. I will wait a little bit for you, because I think there is small delay. Okay. Okay, so at this moment we see the Midas NFX environment, and I will use the analyst mode. So the model type will be 3D, and unit system has been set up to Newton millimeter joule and the second. So let's click on OK. So let's start sketching the geometry. First of all, let's move the work plane to the global zeta x plane. So I'm clicking on this icon, move work plane, and let's select this plane, and let's confirm that using OK button. Now I'm clicking on the normal view. Okay, and temporarily I will hide the grid and datum axis just for the better view. So let me check. So okay, so you're supposed to see everything. So let's start from the sketching the arc. So now I'm clicking on this command. I will use the first method, and let's input the center for my arc. So in this case, let's enter the data 0, -4, and let's click on apply. And for the start location, I will change the method from absolute data XY to reduce and start angle. So I'm clicking on this option and let's enter the value for the reduce. This time will be 25, and let's start from the angle which will be equal to 270 degrees. Let's click on apply, and once again let's click on let's change the method to end angle, and let's specify the end angle. This will be 360 degrees, and click on the apply. So as you see, I just sketched the arc, and let's create two arcs more. So this time I will enter the location. For the center it will be 0, and y will be equal to 24.5. I will use exactly the same procedure, so I will check the radius. Radius this time is equal to 23.5, and starting radius is the same, 270. Apply, and end angle 360. Let's create another arc, 24.5, so it's the same. The center is at the same position, but the radius will be slightly different. So 22.5, start angle the same, 217, and end angle will be 360. Actually, let's back and let's create again, because I think I've made a small mistake. So 24.5 for the center, radius again 22.5 and 270, and end angle 360. Apply. Oh yeah, this time is fine. And let's create the last arc, and this time the location will be defined like 29 on the x direction and -4 on y direction. Let's click on apply. Radius will be equal to 4. Angle will start from 90 degrees and will end on 180. Let's click on apply. Okay, so I just created all of the arcs, and let me sketch the line. So this is my starting point, and let's enter the relative values, 50.0, and let's click on apply. Okay, now I will go to offset command, and we will offset the geometry for the die. So let's enter the offset distance. Let's select the lines. Let's select it even with the arc. Now I'm clicking on the preview so we can investigate the direction for the offset. So I have to uncheck this arc this time and confirm the offset for these two lines. Now I'm selecting the line, and we have to add -1 to offset the arc. Okay, so let me sketch the curves. So now I'm joining offsetted curves, and my sketch is almost done. So this is how does the look like the sketch for the extrusion. Okay, so let's use the isometric one view. Let's display the local coordinate system, and from the protrude commands let's extrude the geometry into 3D. So from the selection toolbar, I'm clicking on the edge. I'm selecting all of the edges. As the length, I'm specifying the value for 25, and direction will be parallel to Y, global Y axis. Let's click on the preview. Okay, and my geometry is almost created. So I'm going to the 3 to the left, and let's hide the curves, and let's display only the solids. I will create sheet metal geometry, so I will use the box, and let's enter the values. So 60 for the length, 15 for the width, and height will be 1 millimeter. Let's display the grid, and let's place the sheet metal in at the center of the coordinate system, directly at 0, 0 position. So I created the geometry for the solid geometry for my model, and at this moment my idea is to use the 2D elements. So I will create the mid surfaces using the make neutral sheet command, and I will use the automatic option. So now I'm clicking on the punch. So let's apply. Now sheet metal, and let's click on the die, and as you see, mid surfaces has been generated. Let's display the solid elements, and of course we can change the color for the geometries. So now I'm hiding the solid geometry, and this will be not needed. If you want, we can join the surfaces for the die. So I will use the Boolean operation, and let's select all of these 3 surfaces. And let's click on OK. So now we have 3 surface bodies. And there is one thing left related to the geometry. I will break the edge for the sheet metal because this will be necessary for the mesh seeding. So I'm using this command, break curve, and from the selection toolbar I'm clicking on the edge. So now I'm selecting this edge, and the value will be 0.33, which means 1/3 of the line. And let's do the same for the second line. Now I will sketch the line for the projection, and using automatic snap option I'm sketching the line. So using the imprint option, I can provide the projection to my geometrical objects. So I'm using the imprint curve. At this moment I'm selecting the sheet metal geometry, and now I'm choosing the this curve as the tool, direction of the shortest path line, and let's click OK. Let's hide all of the curves, and my geometry has been prepared. So at this moment I can go to the mesh, and I can start doing the mesh seeding and pre-processing for the mesh. Okay, so let's assign the size. So for that curve, let's assume 160 elements. For that curve, let's assume 10, 5 elements for the width, actually 3 elements, let's say, 3 elements for the width, and let's mesh it using the map phase. We can preview. So I think it will be better to mesh the surface independently. So let's click on preview, and let's name the mesh for the sheet metal. And at this moment we are not providing any information about the property. This will be added a little bit later. So now I'm clicking on apply. Okay. I think it will be better if we change the size on that edge to 5. So I will overwrite this, and now we can create the mesh for this part of the sheet metal. So let's add this mesh to the sheet metal mesh set, and let's click on apply, and we have the first mesh. So now I'm going to the mesh branch, and let's hide this mesh, and let's hide the geometry body, and let's create the mesh for the die and punch. So let's set up the number of the divisions to 5, and I'm selecting this edge for the die and this edge for the punch. I'm clicking on apply. For these edges, which means this edge, and this arc length, let's enter the 30 and 16 for this edge. And I'm doing exactly the same procedure, so I'm clicking on the 2D map phase, and this time please change the property into 2 and change the name of the mesh set to die. Let's click on the preview, and let's change the mesh seeding on these edges. So I will add mesh seeding, and this will refers to 5, and let's check again the mesh distribution. So at this moment everything looks fine. So once again, let's change the property to 2. Let's change the mesh set to die, and let's click on apply. And let's create the last mesh for the last part, which refers to the punch. Let's change the number for 3. Let's click on this surface. Let's click on the preview, and everything looks good. So let's click on OK. So if we display all of the meshes, our model should look like on the screen at this moment. Okay, now is the time to set up the material data, and to analyze this model. We will use the original material definition and material with the function. So we will start from the definition of the sheet metal material properties. So now I'm clicking on the material, add, and isotropic. I'm clicking on the elastoplastic, and at this moment you're supposed to see the card with all parameters necessary to provide this data. So for the elastic modulus, let's provide the value, for example, 17,000 megapascals, Poisson's ratio 0.342, and let's enter the name, sheet metal. And for the plasticity, we will provide the plastic hardening curve, and to do that we have to click on this plastic hardening function, and via this dialog box we have to provide this data. And I will use my Excel calculation sheet to calculate this data. So this is the Excel file that I prepared. So if we have the data which has been mentioned during the presentation, like strength coefficient, we can generate the curve. So let's provide this data, and this time let's enter the 550 megapascals as the strain hardening exponent. Let's provide 0.225. And as the yield stressed, we can provide 194, for example. So as you see, the curve has been sketched in the Excel automatically. And at this moment, I will make a copy of these columns. Ctrl+C. I will paste that as the values, and I will remove this comment, and from this point I will make a copy of the data which will be valid for anything. So I'm pressing the Ctrl+C. What I made actually is I removed the second column, which refers to the simple calculation, to the calculation from the simple formula, but I had to add the yield stress. That's why in this edge, actually I'm starting from the plastic stress. So this is not necessary, and this data will be valid. So let's enter this data. Okay, I have to change the commas into the dots. So let's paste again as the values, and let's change the commas into the dots. Change everything. Okay, let's close that, and let's copy once again. And now we have the plastic hardening function. Okay, so I'm clicking on OK. Now I'm selecting this plastic function, and all of the data has been provided. We can add mass density if you want, but anyway it will be not considered because there will be no gravity. But in terms, if you want to change the type of analysis and add the gravity, it will be good to keep this value. Okay, so we have this sheet metal, and let's click on OK. And now I have to create two materials which will be related with the punch and die. So let's change the name to rigid punch, and let's specify the values for that. So it will be rigid punch with elastic modulus of the steel, Poisson's ratio 0.3. mass will be the same. So this is rigid punch, apply, and now we need a second definition for the rigid die. So only one thing what we have to do is to change the name and keep the same value. So please click on OK. So you're supposed to have three material definitions, and right now we have to associate them with the properties. So now I will display only sheet metal mesh, and I'm going to the parameters, and I'm clicking on the 2D. So as you see in this option, the default option is the change property, and this is exactly the task what I want to do. So I'm selecting all of these elements. So it will be good anyway if we define the property first. So please excuse me. So let's define the property first. So let's start from this undefined property and let's define them, because we have to add the value of the thickness for the third dimension. So let's change the name first. So this will be sheet metal. Property material is sheet metal, and the value for the thickness will be 1 millimeter. So let's click on OK. And for the second property, let's enter the name for the rigid punch. Let's change the name to let's change the material to the rigid punch and keep the value of 1. Let's click on OK. And the same for the third property, rigid die, and let's click on OK. And we have to change the material as well. Okay, so now we have three materials, and right now we have to go to the parameters and we have to change the properties. So now I'm selecting all of these elements, and from the property I'm associating the sheet metal property with the sheet metal geometry. So I'm clicking on apply. Now I'm hiding the sheet metal mesh. Let's display the die. Let's select from the property die, and let's click on apply. And let's associate the rigid punch property for with the rigid parts mesh. So we can investigate the model. So if we click on the sheet metal, we can check that this highlighted part of the assembly includes the sheet metal material and property, which is correct. If we click on the die, the property and material is also fine, and for the punch we have rigid punch property. So now everything has been defined. And the next step is the definition of the contacts, because the contacts will be used in this model. So now I'm clicking on the contact pair, and let's create the contact pair. So from this dialog box, I will choose the manual contact, and we will create two contact pairs between the punch and die, and punch and sheet metal, and between the sheet metal and die. So let's create the first contact pair. So this will be punch, sheet metal, surface to surface contact. Contact type will be general, and we will create the contact between the 2D elements. So for my case, now I'm I will hide the mesh set for the die and punch, and as the master, I'm clicking on this button, select object, and as the master I'm choosing all of the sheet metal elements. Under the slave, let's display the punch, let's hide the sheet metal, and let's select all of these elements. And let's click on apply. So, and you see the punch sheet metal contact pair has been generated. So if I display the sheet metal and die, we see the blue and red color, which is which describes the contact pair and master and slave respectively. So the first contact pair has been generated, and let's create the second between the sheet metal and die. So this time let's hide the punch. As the master, please check again all of the elements for the sheet metal, and for the die we will select all of the elements as the slave. And OK. So if we display all of these meshes, and if I go to the second contact pair, we're supposed to see all of the contact pairs. Let's check the normals for the 2D. So to check the normals, we can use the front back color. So everything looks fine, especially for the punch and sheet metal. So all of the elements has got good orientation. So let's switch again to the mesh set color. And at this stage, the model is ready to apply the boundary conditions and loading. So now I will save the model. Okay, and let's assign the constraints. So we can do that using the model tree to the left, or we can create the model. We can assign the boundary conditions via the ribbon menu. So let's apply the symmetry constraints first. Okay, so let's change the let's click on this advanced tab, and let's change the name to the symmetry. Symmetry for sheet metal. Okay, and let's hide the mesh for the punch and die. So I will display only sheet metal. So the model is symmetrical along the zeta y. So let's click on this predefined definition, zeta y. And let's check all of the nodes on this edge. But I have to display the body, and let's click on apply. So 6 nodes has been chosen, and let's click on apply. Okay. Let's specify the second constraint, which will refers to the opposite plane. So I'm selecting exactly the same. A comment from the selection toolbar, this will be edge. And I will select all of these 3 edges. And this time we have a zeta x symmetry plane, so let's check it. Let's click on apply. And as well we can constrain the one node here. And we will constrain all of degrees of freedoms except of t zeta. Okay. So if we go to the loads and boundary conditions, we're supposed to have 3 constraint sets. And that's all for the our sheet metal. Let's display the die and punch. And because this punch and die has been created using the rigid element, there is necessary to apply only one constraint at one node. This comes from the definition of the rigid material, and the common mistake which people are doing is that they are constraining all of the edges or some part of the models, but you're supposed to remember that only one node is necessary. So I'm clicking again on the boundary conditions. Let's select the user defined. Let's change the name for the boundary set, and this time this will be punch. And let's select all of degree of freedoms. So I'm selecting this node here. This is the node that I selected. Let's click on apply. And exactly the same constraint definition for the die. Okay. And we're clicking on OK. So we just specified the constraints. And before we apply the dynamic loading, we will specify the function for the displacement. That's why I'm going to this place. I'm right-clicking on the function, and let's create the time function. This function will be used to describe the motion of the punch. So in 2 cases actually, in the loading direction and in the unloading direction. So let's change the name to the loading, and let's enter the values for the loading. So 0 at the time 0, the value will be 0, and in 1 second the displacement for the punch will be equivalent to minus 28.5 millimeters. Let's click on apply. Listen. So we created this function, and let's create another one, this time for the unloading. So we starting from the 1st second. The position is minus 28.5, and the die will back to the initial position during the 2nd second. So this is the unloading function. And let's click on OK. And now we are ready to define the dynamic load. So from this place, let's select the time-dependent nodal displacement, and let's first change the dynamic load set to loading, for example. Let's select the proper time function, loading. Let's uncheck all of these unnecessary degree of freedoms, and let's enter the value 1 millimeter. And finally, let's let's select the object. So I will assign this motion to these constraint nodes. So let's click on apply. Right now let's change the dynamic load set to unloading. The same procedure, time function should be unloading at this moment. There is no need to change the sign because the direction has been described via the function, and let's assign exactly, let's select exactly the same node as the previously, and let's click on OK. So if I expand the dynamic load, we're supposed to have two definitions for the motion, which refers to the loading and unloading, and that's all about the boundary conditions and loading. And finally, we can save the model, and we can go to the analysis case, and we can set up two subcases. So I'm clicking on the other, and from the solution type, let's select the nonlinear quasi-static. So at this case, I will use, let's say, you can say implicit method, which refers to the most popular Newton-Raphson methodology for the calculation of the nonlinear cases. And let's enter the title, loading. And let's create the second subcase. So as the title for the second subcase, let's enter the names. So this will be unloading. We can change the name for the first subcase. So if you press F2 button from the keyboard, you are able to change the title, and this will be related with the loading. Okay, now I'm clicking on the all sets, and from the loading case, I'm removing the unloading dynamic load, and from the second, I'm removing the loading. So exactly, so you see that two cases has been prepared, and at this moment what we have to do is to specify the subcase control data. So I'm clicking on this button. I'm checking the geometry nonlinearity checkbox. My quasi-static analysis time duration is equivalent to 1 second, and as you remember, this has been provided in my function as well. The number of the increments will be equivalent to 50. And this time for the convergence criteria, I will uncheck the work, and I will check the displacement, and to get result, let's say, quicker, with less problems or with the convergence, because actually this type of simulations require a much more finer mesh, and I will reduce the error tolerance to 0.01. And as well, if we go to the advanced nonlinear parameter, we can select the method for the stiffness update. So I'm selecting the full Newton Raphson. Quasi-static has got an arc length method. So this somebody is asking about that. So if you want to use this methodology, we can check this method. This will be necessary, for example, for the nonlinear buckling cases. So we have that. But in our model, I will use full Newton Raphson. Let's set up maximum iterations per increment to 500, and bisection level let's change to the 10. So this will be very helpful to achieve the convergence. So let's click on OK. And that's all for the first subcase. For the unloading case, we are doing similar procedure, but this time we are expecting only the the quality of the result via the displacement, let's say so. So I will check only this option. Actually, I wanted to see, we want to achieve the accuracy via the displacement, so this is our task. So I'm changing this 0.01, and we can set up the number of increments for 100. You can as well increase this number of increments, because this refers to the spring back of the model. So it will be much more helpful with the convergence if the number will be increased, but this should be fine. The geometry nonlinear checkbox should be also checked, and that's okay. So in this case, I showed you how to set up the model to perform simple metal forming simulation. Right now I will open the model which has been prepared previously, but sorry about that, but I forgot about one parameter. So before we solve this model for the calculation, please go back to the contact and let's edit these contact parameters, and let's specify the friction coefficient. This is very important for this type of simulation, because if you don't do that and you can try it by yourself, your model will be converged, but the simulation result will be not valid, and actually your plate will move, let's say, to the space, and and this will be quite interesting. So let's provide the friction coefficients of 0.13, for example, and let's click on OK. So please don't forget about this parameter. And right now I will open the model which has been calculated before. This is exactly the same model, and we will display the results. The simulation type, the only difference is with the model that I made before that we specified much more elements via the thickness, via on the width of the sheet metal, not on the thickness, but the rest is exactly the same. The calculation time is around 25 minutes on my PC, so it's not so time consuming. And let's display the results. And at this time I'm clicking on Insert Analysis Result, and I will click on the Select All button, and let's click on OK. So I will display display the plastic stresses. For example, this factor, shear strain equivalent, actually this is the strain, so sorry about that, but actually we can display even the strain, so this will be quite interesting. So let's set up the interval, let's say every fifth, let's click on OK, set the auto scale to real, and let's display the feature edge. So now I'm clicking on play, and let me show you this again. So we're supposed to click on this Select All button, all subcases, click OK, and right now we're supposed to see the animation for the metal forming. So if I click on this mirror plane and specify the plane for the X and for the second plane, we can see the full model for the shear metal bending. So as you see, let's display the punch, because at this moment it hasn't been shown. And let's use the front view. Let's hide the geometry, and right now we see only mesh. And if we go to the property and if we check this property, I will show you that contact is between the geometry and edges. So at this moment I display the thickness, and the thickness is displayed for the elements, and as far as you know that we use the quarter of the symmetry, the thickness is displayed only for the elements, not for the mirror view mode. So let's show again. So we exactly see that there is a contact between the sheet metal and punch and die. So now I'm unselecting this option. Let's go back to this view, and that's all for today about this sheet metal forming. So if you have any questions, there is a time to answer about it, and we can also provide you some explanations via email. So my email address is piotr.stepian@midasit.com, and at this moment I will write this in the chat section. And here is my colleagues. Address, cyprian@midasit.com, so you can write to us some questions. Of course, we will send you some small survey after this webinar. And at this moment, I would like to say thank you for the joining, and my colleague Cyprian will inform you about the survey, and he will say a few words about it.
Hello everyone, I'm Cyprian. Thank you very much for joining today's session. I hope you enjoyed the webinar, and we will have a small survey that will be sent by email to you with just some few questions about today's webinar, and if you have some idea about subjects for future webinars, because we're always searching for such subjects. So if you have the time, please fill this small survey and help us to find good subjects for the next webinars. So also, I hope you will join the next webinars, and if you have some questions, you can always ask me or ask my colleague Piotr Stepian. Okay, thank you very much.
Yeah, thank you. Goodbye. How it goes?